Right now, at this very second, a decision you make here could instantly change the state of an object on the other side of the galaxy. And I don't mean sending a signal. I don't mean any kind of communication at all. I mean a change that happens immediately, as if the two things are one, connected by a thread of pure information that ignores the speed of light, ignores distance, ignores everything we know about how cause and effect are supposed to work. This is quantum entanglement. And if your brain just screamed, "That's impossible," you're in good company. Einstein called it spooky action at a distance and thought it proved quantum mechanics was wrong. He was wrong. It's real. It's been tested. And the reason it happens is the single most bizarre, beautiful, and reality-shattering idea in all of physics. It doesn't involve invisible strings or secret messages or magic. It involves a truth about our universe that Richard Feynman uncovered. A truth that says a particle doesn't have a history. It has all of them at once. And before we dive into that rabbit hole, if you're the kind of person who needs to know how the universe really ticks, not just the comforting story we tell ourselves, hit that subscribe button. Because on Think Beyond Physics, we don't just describe the weirdness. We show you the logical, inevitable, and utterly mind-bending reason it has to be that way. Now, let's unpack why this feels so impossible. You and I live in a local universe. What does that mean? It means things only affect other things that are nearby. If I want to change something over there, I have to send something here to there, a signal, a force, a particle. And that takes time. It can't happen faster than the speed of light. This isn't just a rule. It's the bedrock of reality as we experience it. It's why you see lightning before you hear thunder. It's why we can look at the stars and see the past. So, when physicists tell you that two entangled particles born together and then flung light years apart can somehow remain linked so that measuring one instantly defines the state of the other, your intuition rebels. It sounds like a magic trick. It sounds like if I flip a coin here and you instantly know whether your coin on Mars is heads or tails. But it's worse than that. In the quantum world, these particles aren't like coins with a secret, predetermined side. Until you look, they exist in a fuzzy superposition of all possible states. They are both heads and tails. The act of measurement, of looking, forces it to choose. And here's the kicker. When you force that choice for one, its entangled partner, no matter how far away, is forced into the corresponding state at that exact moment, not after a light speed delay. At that moment, this is the spooky action. And for decades, even after it was proven in labs, the why was buried under a mountain of mathematical formalism and a collective scientific shrug that basically said, the math works. Don't think about it too hard. But that's not good enough. We need to think about it. Because if we just accept a weirdness, we miss the revelation. The revelation is that our problem isn't with the particles. Our problem is with a much deeper hidden assumption we all make about how reality unfolds. We assume that a particle, or anything really, gets from point A to point B by taking a single, definite path, a history, one story. It leaves here, it travels through space along this specific route, and it arrives there. What Feynman discovered is that this assumption, this one-story universe, is a complete and total illusion. It's a comforting lie our brains tell us to make sense of the world, and to understand entanglement. To see why that spooky connection isn't just possible, but inevitable, you have to be willing to let that illusion go. You have to be willing to step into a world where a single particle on its own is already doing something far stranger than being in two places at once. Before I reveal what that is, you need to understand the trap we've all fallen into, the trap of a single history. To see the trap, let's rewind. Let's go back to the birth of this puzzle, to a man who saw it coming and hated it. The year is 1935. Albert Einstein, the man who had already shattered our notions of space and time, is now deeply troubled by the new quantum theory coming out of Copenhagen. He's working with two younger colleagues, Boris Podolsky and Nathan Rosen. Their goal isn't to explore quantum mechanics. It's to expose what they see as its fatal flaw. They craft a brilliant thought experiment, now called the EPR paradox. Imagine, they said, two particles created together so that their properties are linked like two coins guaranteed to land on opposite sides. You separate them by a vast distance. Now, according to Copenhagen, neither particle has a definite state until measured. But Einstein asks a devastatingly simple question. If I measure my particle here and instantly know the state of the one light years away, Haven't I somehow determined its reality faster than light? And if that's true, either the theory is incomplete, the particles had secret plans all along, like hidden coins with predetermined sides, or we have to accept this magical, spooky, instantaneous connection. Einstein staked his entire worldview on the first option. There had to be hidden variables, a deeper, more sensible layer of reality that quantum mechanics just hadn't found yet. God does not play dice with the universe, he famously said. And for nearly 30 years, this was a philosophical debate, a war of ideas between giants, Einstein on one side, and Niels Bohr, the champion of Copenhagen's weirdness, on the other. It felt like a stalemate. How do you test a thought experiment about reality itself? The answer came from an Irish physicist named John Bell. In 1964, Bell found a crack in Einstein's argument. He didn't build a machine, he did something more powerful. He created a mathematical theorem. Bell showed that if Einstein was right, if there were local hidden variables, if everything was predetermined and no spooky action existed, then certain statistical results for measuring many pairs of entangled particles would have to obey a specific limit, a boundary. But if quantum mechanics was correct in its full spooky glory, the results would violate that limit. They would cross Bell's boundary. This was huge. Bell had turned a philosophical debate into an experiment you could actually do. All someone had to do was build the apparatus, run the test, and count. The race was on. The first truly decisive experiments came in the early 1980s, led by a French team under Alain Aspect. They built a system to entangle photons, separate them, and measure their polarization in ways that could catch any hidden variable scheme in a lie. The setup was mind-bogglingly precise. They had to ensure no signal, no force, no anything could travel between the detectors at the moment of measurement. They even used rapidly switching detectors, so the choice of what to measure was made after the particles were already in flight, eliminating any chance of a secret, pre-planned conspiracy. Think about that for a second. The particles are launched. While they're in mid-flight, the experimenters randomly decide what question to ask them. It's like sending two people to opposite corners of the earth, and only after they've arrived do you randomly decide to ask one of them heads or tails, and the other red or blue, and they still always give matching opposite answers. The results were unambiguous. The quantum predictions were confirmed. Bell's inequality was violated. The universe had chosen. There were no hidden variables, no local reality. The spooky action was real. Einstein was wrong. This was the moment the trap snapped shut. We were forced to accept that either information travels faster than light, or our idea of separate, independent objects is fundamentally broken. But here's where most explanations stop. They say, see, it's spooky, it's non-local, get used to it. And that's where we leave you with a sense of mystery and unease. But that's not the end of the story. That's where Feynman's story begins. Because while Aspect was running his experiments, Feynman had already been working for decades on a completely different way to do quantum mechanics. Not as a set of rules about what you can't know, but as a breathtakingly literal picture of what is actually happening. And in that picture, the spookiness vanishes. It gets replaced by something much, much stranger. But that's not even the strangest part. The strangest part is that to see it, you have to abandon not just locality, but something even more basic. You have to abandon the idea of a single path through history. And to understand why, we need to take a step back from entanglement and look at the most humble thing you can imagine, a single particle, with nobody to entangle with, just moving from one point to another. So let's talk about this single particle. How does it get from A to B? In our classical, everyday world, the answer is obvious. It takes the one best path, the path of least resistance, the shortest distance, the one history you could film with a camera. A bullet leaves the gun, travels in a parabolic arc, and hits the target. One story. But Feynman asked a childlike, devastating question. How does the particle know that's the best path? How does it, at the very beginning of its journey, calculate all possible routes and choose the optimal one? It doesn't. It can't. So Feynman proposed we take the question literally. What if it doesn't choose? What if it doesn't take a path? What if it somehow explores all possible paths at once? Every conceivable way to get from A to B. The straight line, the crazy loopy path that goes via the moon and back, the zigzag, the path where it sits still for an hour and then zips over at twice the speed of light, every single one. This sounds insane. It sounds like fantasy. But Feynman wasn't speaking metaphorically. He built a precise mathematical framework around this idea called the path integral formulation, and here's how it works. He assigned a little arrow, a phase, a tiny compass needle to every single possible path. Each arrow spins as the particle would move along that imaginary path. The speed of the spin is determined by the action, the energy, and time of that particular journey. Now, most paths are crazy. Their arrows are all spinning at wildly different rates, pointing in random directions. When you add up all these arrows for all the insane paths, they tend to cancel each other out. They point everywhere, so their sum is essentially zero. They contribute nothing. But, and this is the beautiful part, near the classical path, the sensible one, something magical happens. For paths very close to that sensible route, the arrows spin in almost perfect synchrony. They line up. They point in roughly the same direction. So when you sum these arrows together, they don't cancel, they reinforce, they add up to a big fat arrow. That big arrow is the probability of finding the particle going from A to B. The particle isn't taking all paths. It's that all paths are part of the calculation of its reality. The sensible path emerges not because it's the only one, but because it's the only place where the universe's accounting doesn't cancel itself out. Think of it like this. Imagine you're in a room with 1,000 radios, all tuned to static. It's just noise. But if you could very precisely adjust the tuning of each radio, you could get them all to broadcast a faint, identical signal. The random noise would still be there, but in the perfect alignments, you'd hear a clear tone rising above the chaos. That clear tone is the particle going from A to B. The chaotic static of all the other paths is still there, underlying everything, but it cancels to silence. This is the first layer of the revelation. A particle doesn't have a position and a velocity. It has a probability amplitude, that sum of arrows spread over all of space, for all possible histories. Now I want you to hold that image in your mind. A reality not of things, but of swirling clouds of potential, of every possible story being told simultaneously, with only the coherent ones rising to the level of what we call real, because we're about to add a second particle. And this is where your brain might explode. When you have two particles that have interacted like the ones we use for entanglement, their stories, their histories, are no longer independent. You cannot assign one history to particle A and a separate history to particle B. There are no longer two separate sets of all possible paths. There's only one set, the set of all possible joint histories. The sum-over-histories now has to consider every single way the pair of particles could have gotten to their final destinations. Every intertwined, coordinated, dancing path of the duo. They are inextricably linked in the accounting of reality. They are a single quantum system described by one grand probability amplitude. So when you finally separate them and take them to opposite sides of the lab or the galaxy, that mathematical link isn't broken. How could it be? Their possible histories are still woven together in that underlying cloud of potential. Measuring one particle isn't sending a signal. It's performing a drastic simplification. It's forcing the entire gargantuan two-particle sum-over-histories to collapse down to a subset that is consistent with your measurement. You're not poking one independent thing. You're poking one corner of a single, inseparable pattern. And when you do that, the entire pattern instantaneously reconfigures itself to be consistent. There's no travel time, because there's no distance within the pattern. The distance was an illusion of the particular classical history that happened to get reinforced. The deeper reality is non-local, because it was never built out of local, independent parts to begin with. It was built out of global, entangled possibilities. Stay with me here, because what I'm about to show you is the real reason this matters. This isn't just a clever math trick. This is what reality is. And to prove it to you, we need to see what happens when we try to fight it. We need to see what happens when you try to use the spooky connection to send a message, to break the speed of light. You'll find you can't. And the reason you can't is the final beautiful piece of the puzzle. So, if the connection is instant, why can't we use it to send a message faster than light? This is the ultimate sanity check. Let's walk through it with our entangled pair. Imagine we have our two photons entangled so that if one is polarized vertically, the other will be horizontal, and vice versa. You take one to Mars. I keep one on Earth. We agree that if I want to send you a 1, I'll force my photon to be vertical. That should instantly force yours on Mars to be horizontal. A binary signal, the dream of science fiction. But here's the catch, and it's a subtle one that reveals everything. On Mars, you have a detector. You look at your photon. What do you see? You see it is either horizontal or vertical. But you have no way of knowing which state it was before you looked. Remember, in the quantum world, until measured, it wasn't either. It was a superposition. So when you get a result, say, horizontal, you cannot tell if it's horizontal because I just made mine vertical, or if it was always going to be horizontal because that's just how this particular pair happened to be. From your perspective on Mars, your photon behaves exactly like a random coin flip. Half the time it's horizontal, half the time it's vertical. You see no pattern, no signal, just noise. To see the spooky correlation, you need something else. You need to compare your list of results with my list of results back on Earth. You need to bring the two data sets together, and that comparison can only travel at the speed of light. The magic is in the correlation, not in the individual outcomes. And this is not a technological limitation. It's baked into the heart of quantum mechanics. The randomness of the individual measurement is the universe's way of preserving causality, of preventing paradoxes like messaging your own past. It's the cosmic firewall. Now, let's connect this back to Feynman's picture. In the sum-over-histories, when I measure my particle on Earth, I'm not selecting a single history for it. I'm selecting a subset of all the possible joint histories, the ones where my particle's outcome matches what I saw. That subset still contains every possible history for your particle that is consistent with my result. From the perspective of the total amplitude, your particle's cloud of potential hasn't been zapped into one state. It has been correlated with mine. Its probabilities have been updated globally, instantaneously. But until you actually perform your measurement, that update is just a reshuffling of possibilities. It doesn't produce a definite observable fact for you until you look. And when you do look, from your local perspective, you just get one random result from that newly correlated set of possibilities. No signal was transmitted. The global pattern simply became consistent. Wait, it gets even weirder, because this framework makes a prediction that seems even more outrageous. Let's do a thought experiment. Imagine we don't just measure our particles for simple vertical or horizontal polarization. Let's get clever. Let's say you on Mars can choose at the last second to measure your photon's polarization at any angle, maybe 0 degrees, vertical, 30 degrees, or 60 degrees. I on Earth can do the same. We don't coordinate our angle choices in advance. Now, if there were hidden variables, little secret plans the particles agreed on at birth, there's a mathematical limit to how often our results will agree when we choose different angles. This is Bell's inequality again. But in the quantum world, in Feynman's world of intertwined histories, the correlation is stronger. Why? Because the particles aren't following a plan. They are parts of a single system whose final outcome depends on both of our last-second choices. My choice of measurement angle here doesn't just force my particle into a state. It influences which subset of the grand entangled history becomes relevant for your particle, given your chosen angle. The correlation is baked into the global structure of reality, not carried by the particles. It's as if the universe, at the moment of the pair's creation, didn't prepare two objects with instructions. It prepared one single, non-local recipe that says, if Earth asks this question and Mars asks that question, here is how the answers shall relate. The questions themselves become part of the event. But we're not done yet, because this leads us to the deepest, most philosophical implication of all. If this is true, if the properties of particles aren't determined until the moment they are measured, and if those measurements on entangled partners can be space-like separated, meaning there's not even time for a light signal to connect them, then what does now even mean? In relativity, there is no universal present. What's now for me on Earth is a mix of past and future for you on Mars, depending on your state of motion. So if my measurement defines the state of your particle, and from my perspective that happens instantly, from another observer's perspective moving at high speed, my measurement might actually occur after yours. Who caused what? The beautiful, almost unsettling resolution from the sum-over-histories perspective is that cause and effect in the classical sense begin to blur. The universe isn't computing a chain of causes. It's evaluating consistency across the entire four-dimensional block of spacetime. It's asking, given the boundary conditions, the creation of the pair here, and the final detections there, what are the self-consistent histories that connect them? Our insistence on a linear narrative of I did this then that happened is another classical illusion. The reality is a vast interconnected web of amplitude where before and after are less fundamental than consistent with. This is why Feynman's revelation shatters your reality. It doesn't just explain entanglement. It suggests that the universe at its most fundamental level isn't made of things bouncing around. It's made of events and relations. Particles aren't tiny billiard balls. They are more like temporary knots of consistent probability, where the threads of every possible history weave together into what we perceive as a solid object. Entanglement isn't a strange connection between separate knots. It's the evidence that the knots were never truly separate. They were always part of the same fabric. So why does quantum entanglement happen? Let's bring it all together into one clear, devastatingly simple picture. It happens because the most fundamental description of our universe is not a collection of objects with defined properties traveling along single, definite paths. It's the crude, approximate story that emerges for things like baseballs and rockets. The fundamental description is a vast, shimmering cloud of potential, a sum over every single possible way that every single particle could have interacted, moved, and been measured. In this cloud, particles that have once interacted never truly divorce. Their possible futures remain mathematically intertwined, described by one single, indivisible probability amplitude. When you separate them by distance, you aren't stretching a connection. You're just observing the same inseparable pattern across a wider region of space. Measuring one isn't sending a signal. It's making a particular thread in that pattern visible, and in doing so, it instantly defines which other threads are now consistent with that observation. The spookiness vanishes when you realize there were never two independent spooks. There was only ever one non-local reality. Entanglement isn't the weird exception. It's the default state of the universe for things that have interacted. What's weird is the isolated, independent existence we think we see. That's the illusion. Feynman's genius was to take the mathematical formalism of quantum mechanics and give it this breathtakingly literal interpretation. To calculate the probability of any event, you must literally add up the contributions from every possible history that could lead to it. And in that every possible history, the idea of separate local objects living their own lives simply doesn't exist. They are all part of the same grand story. So the next time you hear about particles communicating faster than light, remember, they aren't communicating. They are not separate entities to begin with. They are two aspects of a single, deeper truth. A truth where the past, the present, and the possible are all woven into one consistent whole. The universe isn't performing magic. It's just doing the accounting. And the balance sheet is global. This is the beauty of physics. Not comfort, not simplicity. Truth. And truth, it turns out, is a tapestry woven from every story that could possibly be told, with only the consistent ones shining through as the world we get to touch. Entanglement isn't a bug in the universe. It's a feature, a direct glimpse into that foundational tapestry. It forces us to trade our childish map of separate things for the breathtaking, complex, interconnected territory of what actually is. Now I want to hear from you. What part of this broke your brain the most? Was it the idea that a particle doesn't have a single history, or the realization that spooky action is just our shock at seeing non-locality for the first time? Drop a comment and let me know what you're still wrapping your head around. I read every single one. And if this video made you see the universe less as a collection of billiard balls and more as a single coherent pattern, share it with someone who still thinks spooky action is just a mystery. Let's blow some minds together. Next time we're tackling time. Not time dilation, not the arrow of time, but the question of whether time itself is even a fundamental thing, or just another illusion emerging from this same web of quantum possibilities. And trust me, if you think this was weird, you haven't seen anything yet. That's the beauty of physics. Not comfort, not simplicity. Truth. And truth is always stranger than you think.